Okay, now we have the following rules in our mind. These are empirical rules or sort of heuristic rules. So, going ahead in the same thread of thought, how do we build prior information into a neural network? So, there are some ad hoc procedures. One would be restricting the network architecture through local connections, right. We have certain local connections and we restrict the network architecture through local connections. The other would be by constraining the choice of synaptic weights through weight sharing. And when we talk about when we discuss convolutional neural networks, we will talk about what this weight sharing idea is, right. So, you have a portion of the network and you have some weights that go to one part of the network, and these are what I call local connections. Similarly, we have for the bottom part, and then this weight is going from three to 1 and this is going from 3 to 2, right, and the same weight is being shared between two parts of the network, and this can help bring local features within the network that you can kind of share, and therefore you can bring in some prior information within this network. This is really an ad hoc choice and there is no clearly what is the science behind incorporation of prior information to neural network. These are some procedures and we fold these procedures into mathematical formulation and let the network learn from these. Okay. Another concept, building invariances into neural network design. How do we build invariances within the design of a neural network? So, let us start with a simple example. So, I have this shape of a man, right, it's an Egyptian symbol. So, let us say this is A, just straight upright, this is tilted with a negative angle of 30 degrees, perhaps upside down, right, you just turn it upside down. When we perceive all these images, we think they are the same. Our visual system perceives all these invariances to be the same. How can we make a neural network learn these invariances, right? We perceive A through C to be the same, how can a neural network take care of this, right? Because if you recall what our objective is throughout the course, we want a machine to learn what a human can do, right? What a human brain can do, we want a machine to learn this. And if we want this to happen, how do we extract this information and make a machine learn this information? Through learning rules driven by an objective function. So, from our basics of coordinate geometry, we can say that the features from A through C, they are all linked via the rotational transform R, which is given by cos theta minus sin theta. This is sin theta and this is cos theta. This is the rotational transformation. So, if I give you the original coordinate space in this way, right, through a rotation of the coordinate axis, you can have a different representation, right. So, if we were to extract features, we have to extract features that are rotationally invariant, right. So, this is one of the ideas, or else you have to design the geometry of the neural network in such a way that these invariances are naturally folded within the network. So, let us look into two invariance ideas. One is invariance by structure, the other is invariance by training. So, let us see these ideas, what they are. Transformed versions of the same input are forced to produce the same output. For example, going back to our previous slide, right, if I have object A and I extract some features out of object A and I present it to the network and I say that the desired response is 1 for object A. Similarly, I rotate this object by an angle theta and I extract the features and I present it, I say that this also has to be the same desired response, right. And if we force the transformed versions of the same input to produce the same output, then we sort of bring in this invariance through structure. Suppose Wji, so I will remove this comma, so we kind of are familiar that there is this neuron I which connects to J, and that is sort of the implication. Suppose Wji is a synaptic weight of neuron J connected to pixel I. If Wji is equal to Wjk for all pixels I and k lying equidistant from the center of the image, we are naturally forcing rotational invariance within the design of the network. Similarly, we can think about translations, we can think about scaling, right. You may have an enlarged image, and if you have an enlarged image, you have to capture the local receptive field through some mask or a filtering operation and slide this operation across the entire image and then extract this information and then build these invariances, or there can be a time or a space translate, right, even that has to be folded in. So, translations, rotations and scaling, these are all important features from our transformations from the original feature set, and these invariances have to be folded within the design of the neural network. So, let us go into the other invariance, which is invariance by training. So, let us start with an example. Call this class A, and then I have this is class B. Now, if we just look at these two classes, at least visually we can think that this is a circle, this is an ellipse, this is also possibly a closed curve, right, and the edges are not possibly straight, right. We can get that information. This is prior information that we get. If we observe class B, we say this is a square, and the square is basically, this is a rhombus, but again a square which is tilted by a certain angle, and then we have this arrowhead. Arrowhead is also a quadrilateral, right, it has 4 sides. Now, if you look at class B, right, there are all straight edges across all these shapes and we do not have smooth curves, whereas if you look at class A, there are it is basically you have these curves connecting these points. So, can we learn the different aspects of the same object under the transformation, right, this is the question. Can we learn different objects or I would say aspects of the objects aspects of the same object under transformations, right. So, can we learn different objects or aspects of the same object under transformations? So, this is very important because our brain can recognize these objects within class A to be the same, and we can perceive objects within class A to be the same and objects within class B as the same, but if we were to make a machine do this, can we incorporate that within our design. So, this is an important invariance that we have to learn through training. Okay. So, then we will get into the other idea about what an invariant feature space is. Again, our guiding force would be examples. So, an invariant feature space is basically invariant to transformations of the input space. We already saw some invariants in terms of rotational transformation, right, because you take the same object, you rotate by a certain transformation and it is invariant. But this is not a simple, this is simple transformation, a linear transformation, but we can think about nonlinear transformations of the input space. And if you were to transform the input space nonlinearly, under these nonlinear transformations can we bring in invariances, right. This is an important idea. So, we will revisit the example that we considered in the very beginning regarding this pattern classification problem, where we had odd and even integers on a line and we wanted to separate those, and with that motivating example we will try to understand this idea. So, what do we want here? We want to extract those features that capture the information content of an input data set, right. So, we will see this, we will revisit the example we considered. If you recall, we had all these crosses and circles. So, I will use a different figure here. A different color, okay. So, we have these crosses in red and we have the circles in green that are interspersed between these crosses, right, and I want to separate them. So, this is equivalent. So, if I lift, I mean your intuition would tell you that if I can take all these crosses out and I just translate them vertically, then I can separate them, right. So, putting this in a more concrete way, so I leave the circles the way they are and I take these crosses and I just lift them up vertically, right. Let us imagine that there is a transformation that can take data points on a line to something possibly on a plane, right. This is on a line, this is on a plane because you have a y coordinate for the crosses, right. If I can do that, then I am not destroying the information content, but through some transformation I am capturing this invariance and then I am letting this machine to learn this. So, this is the idea behind invariant feature spaces. So, how can we do this? This is a question as we try to answer this question through the rest of the course. So, what are the advantages in having invariant feature spaces? One, the number of features applied to the network may be reduced. You do not have to give lot of features to recognize them, but you can take a subset of the features under the transformation and feed this to the network. Obviously, the requirements on the network design is relaxed, right. So, these are the major advantages, and because of which you can have invariance of all objects under the transformation and you are assuring this invariance naturally folded within the design of the neural network, and therefore this is important for our pattern recognition problems. Okay.